I'm doing your home experiment. Have a close look. Heating this reddish metal, copper, converts it to a black powder. But what would I need to convert the black powder back to metallic copper? In these hills, here in Hampshire, there are Bronze Age sites. Now, Bronze Age people made elements, although, of course, they didn't appreciate that what they were making were elements. This green mineral is malachite, copper carbonate. And Bronze Age man had the means to convert this to the element, metallic copper. He did this by pouring the malachite onto a furnace, which was constructed of clay and fueled with charcoal. It reached a temperature of nearly 1,000 degrees Celsius. At first, the malachite decomposed to produce the black substance, copper oxide. And as that reduced, it formed shiny metallic globules, and the copper slowly ran to the bottom of the furnace. It's about an hour since I put the malachite in the furnace, and here, in the hottest part where the bellows were, there's a small globule of liquid copper formed. As I scrape the oxide away, you'll see it shining. And it's so hot that it quickly oxidizes again. There are other rocks that can be smelted in this way. These shiny black crystals are the mineral cassiterite. It's an oxide of tin, a heavy ore that's found in Cornwall. Well, when we take cassiterite and smelt it in a furnace like this is what we find. In amongst this slag, we can find pieces of tin, a shiny metal, which is rather soft. But if we take about 10% tin and melt it with some copper, we produce a new substance, the alloy bronze. Now, bronze is very hard, and it can be used to make things like this. A spearhead about 3,000 years old. It's not so easy to make a new element in the 20th century. We're looking at fuel assemblies being put into a nuclear reactor. Uranium in the fuel gets converted to the new element, plutonium. But what has plutonium, which was discovered in 1942, got to do with the Bronze Age elements, copper and tin? You'll see as the program develops. I'm standing here in the present. Each of these dots represents an element. Like plutonium, these 30 or so have all been made by nuclear reactions. And who's to know what elements will be made in the future and by what techniques? Now, you may be wondering what I'm doing perched up here. Well, there are more than 100 known elements, and I want to give you an impression of how the number of known elements has increased over the years. Suppose we take a walk back in time. 1900, 1850, 1800. So this is a graph of the number of known elements against the year. And here are the elements that were known in prehistory. They include copper and tin. Now let me make a big jump into the 18th century. At first, the discovery of elements was slow, until the second half of the 18th century, when we find this abrupt rise in the curve. We'll notice several abrupt changes like this, and we'll be concentrating on some of them. Why did this one occur in the 18th century? If you were to walk into an 18th century laboratory, what would you see? Well, you would find apparatus designed specially to do chemical experiments. And particularly, at this time, you would find glass-blown apparatus, bulbs and tubes designed specifically to handle gases. And so chemists looked almost naturally at the air around them. Here's how they made poisoned air. The water rises, and the gas that's left is about 4/5 of the original. Well, it not only extinguishes flames, but it kills mice and other forms of life. It's more difficult to separate the gas which supports life. In 1772, Priestley did this by focusing sunlight with a lens onto this orange powder. It's mercuric oxide. The sunlight is focused to a small spot, and if we look closely, what appears like a landslide is liquid mercury being formed. And the other product is a gas. He collected the gas that's evolved. Things burn very strongly in it. Of course, it's oxygen. And the gas that was left after the flame was extinguished, well, that was mostly nitrogen. In 1776, Priestley read a paper to the Royal Society. The air is not an element. There exist several species of airs, essentially different. So, these discoveries of oxygen and nitrogen appeared to complicate chemistry. Air was no longer a simple substance. But as new elements were discovered, patterns began to emerge which helped to group the elements together, which even at the end of the 18th century were becoming numerous. Here's an experiment that was done in 1774. Take some hydrochloric acid, and I'm going to add it to some black manganese dioxide. I'll leave that to react. The gas that's being produced is chlorine. There are two similar elements. This red liquid, bromine, discovered in 1826, and black crystals, iodine, discovered in 1811. These three elements, chlorine, bromine, and iodine, may have more in common than you think. They all occur in the sea. Chlorine, made from hydrochloric acid, which we get from rock salt, originally from the sea. Iodine was discovered in seaweed. Now, if we dry some of this seaweed and then convert it to an ash by burning it, take some of this ash and add concentrated sulfuric acid to it. Well, the reaction takes a few minutes, but now you can see that the purple gas which is produced is iodine, and it's cooling to give shiny black crystals. Well, bromine too can be made from the sea. If we take chlorine and bubble it through seawater, well, you can see how the red substance bromine is giving that orangey color to the liquid. These three elements, chlorine, bromine, and iodine belong to a family because they turn out to have rather similar properties. For example, they all react vigorously with sodium. Here's the reaction of sodium with chlorine gas. This reaction tells us why chlorine, bromine, and iodine are called halogens. They all react to produce salts, and this is one way to make table salt. There you saw an experiment with the reactive metal sodium. In our graph, there's an enormous rise here with the discovery of sodium and potassium, two of the elements in the family known as the alkali metals. This began in the autumn of 1807 at the Royal Institution in London with the impact of the brilliant young scientist Humphrey Davy. Through lectures before invited audiences, he demonstrated dramatic new experiments, often the subject of his own research using this new invention, the chemical battery, a series of copper and zinc plates immersed in acid to provide an electric current. Well, the invention of this provided the answer to many problems in chemistry, and Davy already knew that solutions of salts and other substances conducted electricity. Here's hydrochloric acid decomposing into hydrogen at the cathode, and at the anode, chlorine. But alkalis seem to defy decomposition. In this experiment, from the electrolysis of an aqueous solution of sodium hydroxide, we get hydrogen and oxygen. To Davy, it appeared that the presence of water somehow prevented the decomposition. So he decided to try to electrolyze solid alkali this way. Potassium hydroxide has been melted, cooled, and tipped out of a dish. We're passing a direct current through the fused mass, and you can see that the result is a fierce flame at one of the electrodes. That's potassium burning away in the atmosphere as soon as it's formed. Even today, at the Royal Institution, we couldn't repeat Davy's observations, in which he claimed to have made globules of metallic potassium, and even tipped them into water. But just a year after his discovery, a much more practical way of making potassium was invented, in which potassium carbonate is reacted with charcoal at great heat in a cast iron container. However, Davy's method did show that the electrolysis of fused salts could be used to make new elements. And he went on to make the alkaline earth metal calcium, initially in the form of an amalgam with mercury. First, Davy mixed moist calcium hydroxide and mercuric oxide and placed the mixture on a platinum plate connected to the positive pole of a powerful battery. He used a platinum wire, dipping it into a pool of mercury as the other electrode. Look at the disturbance in the mercury. That's the calcium being formed and producing an amalgam with the mercury. The amalgam prevents the calcium from burning in the atmosphere, and this experiment was much easier to repeat. After the use of electrolysis, the discovery of new elements was slow, and there was a big gap until 1860, when cesium was discovered. Again, this was the first of a series of discoveries which relied on the techniques which had been developed to a fine art in the 19th century for the analysis of rocks and minerals, techniques like the blowpipe. Dissolving in acid. Selective precipitation. Crystallization. And gravimetric analysis. These were used to isolate pure salts from the complex mixtures which occur in some minerals. It was the collaboration of two German scientists, Bunsen and Kirchhoff, which produced this combination, the Bunsen burner and the spectroscope. The burner to provide a hot enough flame to excite the atoms, and the spectroscope to disperse the light. Turning aside all other work, Bunsen and Kirchhoff began to investigate the spectra of minerals which they thought contained the alkali metals, because they believed that the family of alkali metals which Davy had worked on, lithium, sodium, and potassium, was incomplete. Bunsen wrote to one of his fellow workers, Roscoe, saying, "Kirchhoff and I are engaged on a work which does not let us sleep." Well, their hard work soon brought results. They looked at a sample of Durkheim mineral water and extracted a substance which gave this flame. In the spectrum of this flame, they saw two blue lines very close together. And they made this announcement: "There is no simple substance known which gives two such rays in this part of the spectrum. One may therefore conclude the certain existence of a simple, unknown substance belonging to the group of alkali metals." And they called the substance cesium, after the Greek name for blue sky. Notice how confident they were that the presence of just these two lines in the spectrum proved that they were dealing with a new element. Well, spectroscopy continued to provide evidence for the existence of new elements, and on one occasion, from a most surprising source, the sun. To take the spectrum, what we need is a spectrograph, and that's downstairs in the laboratory. To get the light from the sun into the spectrograph, we follow the sun across the sky by tracking a mirror. And that reflects the light to another mirror and down into the laboratory. So if the sun comes out, let's go and see what the spectrum looks like. I've been waiting patiently, and now the sun's shining, so I'll cut out the daylight. Remember, we've got the sun shining down through the roof. It's reflected as another mirror, and across here to the spectrograph. And we can focus the image of the sun on a card. Right, we've got some wispy clouds drifting across the sun. And if you come close in here, you'll see sunspots, lots of them. Now, if we want a spectrum of the sun, I'll take the card away, and we'll put the light into the slit of the spectrograph. So we see absorption lines in the sun's spectrum, these black lines. If we want to look at the light that's emitted by the atmosphere of the sun, well, first we have to get rid of the light from the luminous center. The only way of doing that is to put something between us and the sun, the moon, for example. So we need a solar eclipse. There was a total eclipse in India in 1868. And the English spectroscopist Lockyer looked at the spectrum that was produced in this total eclipse. He identified a line in the yellow region of the spectrum quite close to the sodium D line. But it was a line that was not emitted by any known element, nor was it seen in the absorption spectrum of the sun. He attributed this line to a new element, which he proposed to call helium, from the Greek word helios, for the sun. Now, Lockyer didn't know what this substance helium was. In fact, it's a gas, and I've got some here in this discharge lamp. And so we can see, using this spectrograph, what the spectrum of it looks like. And there's the yellow line that Lockyer saw in the sun's emission spectrum. In fact, this substance, helium, is present all about us in the atmosphere. Like the other gases in the atmosphere, it's colourless, but it has some rather special properties. Nobody's yet succeeded in getting it to react with anything. It's chemically inert, so how was it ever discovered in the atmosphere? Well, from these spectroscopic discoveries, we have to jump 25 years to the realization that helium was not confined to the sun. And here we find the emergence of an unsuspected group of elements: neon, argon, krypton, and xenon. Like helium, they are also gases present in the atmosphere and chemically rather unreactive. Their discovery began with a puzzling observation that the gas from the atmosphere, which had been supposed to be nitrogen, had a higher density than nitrogen from a chemical reaction, for example, from the decomposition of ammonium nitrite. Well, this puzzle was solved by William Ramsay, professor at University College. After removing the oxygen and the nitrogen from the atmosphere, he was left with a residue, no more than 1% of the original. What was it? Well, by now, another technological advance had made this available: liquid air. With liquid air, Ramsay was able to distill this residue, and over a period of 4 years, showed that it contained 4 new elements. You can probably guess how he showed that each was a new substance. For example, here's the spectrum of neon. If we fill a glass tube with neon gas and pass an electric current through it, of course, it glows red. Each of these gases provides a different colored emission. So inert as they are, they still have their uses. That brings me back to the last step in our curve, the artificial elements like plutonium, which can be made in nuclear reactors. As I've been progressing along this curve, I've been picking out the steps, and with each of them we've recognized the introduction of some new technique. Nuclear reactions. The distillation of liquid air. This step I've left to the broadcast notes. Spectroscopy. Electrolysis. Glassware to handle chemicals, especially gases, and the smelting of ores. So we've been looking at how the elements have appeared at different times as groups because of different techniques. And in the next program, we'll be looking at a more fundamental reason for grouping the elements.